Hey everyone and welcome. Today we're going to dive deep into the incredible chemical journey that takes a simple piece of rock and turns it into a gleaming bar of pure gold. It's an amazing story of brute force, incredibly clever chemistry, and just pinpoint precision.
So, let's get right to it. How in the world do you actually do it? How do you take a chunk of what looks like totally worthless rock and transform it into a dense, valuable bar of pure gold? Well, that's the puzzle we're going to solve today. And trust me, the answer is way more fascinating than you might think.
So first things first, the biggest challenge right out of the gate is that gold is incredibly elusive. We're not just walking around stumbling upon shiny nuggets. We are literally solving a massive needle in a haystack problem, but on a geological scale.
To really get your head around this, a typical chunk of gold ore might only have about 1.5 grams of gold for every metric ton of rock. That is 1.5 grams for every million grams of waste. To picture that, imagine trying to find one single specific grain of sugar in a 2-pound bag of flour. The scale of this challenge is just immense.
Now, to make things even trickier, not all gold ore plays by the same rules. On one hand, you've got free milling ore. That's the easy stuff, where the gold particles are kind of just sitting there, exposed and ready to be grabbed. But then you've got the real villain of our story, refractory ore. Here, the gold is physically and chemically locked inside other minerals, almost like it's sealed in a microscopic vault. You just can't get to it without some serious chemical muscle.
So how do we start cracking that vault? Well, the very first step is just a massive physical transformation. We have to break the ore open with brute force before we can even think about picking the chemical lock.
This whole process is called comminution, which is really just a fancy word for smashing things into smaller and smaller pieces. It starts with pure power. Giant crushers take boulders the size of a small car and break them down. Then, those rocks get fed into these enormous grinding mills. Picture these giant rotating drums filled with heavy steel balls. They just tumble and smash the rock over and over until it becomes a fine powder, almost like flour.
So you might be asking, why go through all that trouble? Why turn solid rock into dust? Well, it all comes down to one thing: maximizing surface area. By turning that rock into a fine powder, you're exposing as many of those microscopic trapped gold particles as you possibly can. It's all about preparing them for the chemical bath that's coming next.
And that brings us to the absolute heart of the whole operation: cyanide. And this isn't some newfangled tech, it's a chemical masterpiece that's been the industry standard for well over a century.
This is what just blows my mind. The main process that we still use today was patented way back in 1887. And yet here we are, and it is still the dominant, most effective chemical method for getting gold out of the ground. That kind of longevity is just about unheard of in industrial chemistry. It's wild.
So the chemical step here is called leaching. We're essentially using a special solution to selectively dissolve only the gold, pulling it right out of the solid rock. The best way to think of it is that cyanide is the chemical key that's perfectly shaped to unlock the gold, allowing it to be carried away in water while all the worthless rock gets left behind.
And the recipe for this magic potion is surprisingly simple. On the surface, you've got your powdered ore, you've got water, and you've got cyanide. But there are two secret ingredients you absolutely cannot forget. First is oxygen. Without it, the whole reaction just doesn't happen. And second is a high pH. The mixture is kept highly alkaline, usually with lime, because that is a critical safety measure that prevents the cyanide from turning into a very dangerous gas. It's a precisely controlled chemical cocktail. Okay, so we've done it. Our gold is now dissolved in a huge tank of cyanide solution. But our mission is not over. Now we have a new problem. How do we get that tiny amount of liquid gold back out of the solution and turn it back into a solid? Well, there are two main ways to do this. The old school method is called the Merrill-Crowe process, and it uses zinc dust to basically force the gold out of a clear solution. But the modern workhorse, the real champion, is the carbon in pulp, or CIP process. This method is brilliant because it works directly in the muddy slurry of ore in solution. It uses these little granules of activated carbon to pull the gold right out of the mix.
So how does this activated carbon work? The best way to picture it is as a kind of magnetic sponge that's only attracted to gold. The activation process creates this insane internal network of pores, giving it a massive surface area. And that surface just grabs onto the gold cyanide complex, sucking it right out of the solution. It's incredible stuff.
All right, we've caught the gold on our carbon sponges. We are so close. Now it's time for the grand finale, the final fiery climax of the whole process:
forging the bar.
First, we have to get the gold off the carbon. That's done with a hot caustic solution in a process called elution. This gives us a highly concentrated gold liquid, which is then sent to an electrowinning cell. There, an electric current is run through it, causing the pure gold to plate onto steel wool. Now, finally, that collected solid gold is ready for the furnace.
We're talking about melting this stuff down at an intense 1064 degrees Celsius. It's incredibly hot. The gold is mixed with chemicals called fluxes, and in this extreme heat, the heavier gold sinks to the bottom, while all the lighter junk and impurities float to the top as this glassy layer called slag, which they can just skim right off.
And the final pour creates what's known as a doré bar. Now, this is important. This is not your pure 24-karat gold bar just yet. It's a semi-pure alloy, usually about 90 to 99% precious metals. Think of it as the mine's final product, which is then shipped off to a specialized refinery for the final purification steps to get it perfect.
But you know, the story doesn't end when the gold bar is poured. Using powerful chemicals like cyanide on such a massive industrial scale leaves behind a pretty significant chemical footprint, and that footprint has to be managed responsibly.
You absolutely cannot just dump the leftovers. Effluent treatment is a critical, non-negotiable part of any modern gold mine. Priority number 1 is cyanide detoxification, destroying any leftover cyanide in the waste. Beyond that, other heavy metals that got dissolved have to be removed, and massive amounts of water are recycled to keep the environmental footprint as small as possible.
And because cyanide, for all its brilliance, is still a pretty potent chemical, the global search is always on for greener alternatives. Researchers are looking into all sorts of other chemicals, and thiosulfate is one of the most promising. While it's not quite as cheap or efficient as cyanide just yet, it represents a potential future for a more sustainable way to unlock gold.
And that really leaves us with a final, crucial question for the future. Most of the world's easy, free-milling gold, it's gone. We're getting more and more reliant on processing these complex, tough, refractory ores. So as we move forward, the biggest challenge isn't just finding the gold anymore. It's figuring out how to extract it cleanly and safely. The question for the next generation is this: can chemistry deliver a brand new, greener key to unlock the world's hidden gold?